Welcome to Radar System course. Today we continue a new topic, limitations to MTI performance. So what are the various limitations are there for the MTI radar that we will see, and what improvement factor is to be needed to consider the improvement in the MTI radar there. Okay, performance of the MTI radar. So we need to understand that what will be the improvement factor, and that improvement factor generally depends upon that a signal to noise ratio we say. But here in the case of a radar, noise is nothing but to be considered as clutter. So to remove the noise or to remove the clutter, the what factor is to be considered, or to improve the signal to noise ratio of an MTI radar, and that signal to noise ratio, that factor will be affected by various factors. So what are those factors that will affect a signal to noise ratio of a MTI radar? So generally we have learned that a Doppler shift, and we have seen that. So there are the various clutter, various types of noise is present. So if you see the performance of a radar there, in that case we are getting the signal, that information is nothing but to be called as a clutter. Okay, if you see the frequency response of a received signal, so it has a clutter, then it has some sort of a noise is present here. There will be the noise. This factor is called as a noise. And then we supposed to consider that there will be a small target. So this factor will be considered as a target now. Okay, so we'll consider that this will be a positive PRF, this will be the negative PRF. So now our aim is to remove the clutter as well as the noise. So to remove the clutter, we need to use a filter that is called as a delay line canceller, and then we will remove the clutter, as well as we need to remove the noise. To remove the noise, we are supposed to consider one particular threshold value or a threshold level, so that we can easily identify or easily understand what will be the a target there. Okay, so now this factor will be removed, so we'll get the target. But in general, what happen if supposed to be your radar is moving? Okay, so we can say that a moving platform, your target is moving as well as the radar is moving. So in that case, the performance will be a different. For the stationary object, you will see that this one is a form of a clutter. Okay, this is a clutter for the stationary object, and then somewhere we will see there will be the a target. This one is nothing to be a target. This everything is happen for what if we have a stationary target. But if our radar is moving, in that case, the performance will be different. Due to the moving target, the clutter information we are getting here, this is nothing but a clutter, and somehow we are getting a target information. This belongs to the a target. So generally we say that this one is a clutter and this is nothing but a FD. So likewise we have a clutter and we have a FD. So now we need to identify where is our target. So for that purpose, so your signal we have received. Okay, we need to change the reference of this clutter, or we convert your signal in the form of a stationary object. So for this purpose, we supposed to move the reference. Okay, this one we have a clutter, and this one is supposed to be your target now. Okay, this one is supposed to be will be a target, and this will be a clutter. Okay, so we need to change the reference, and then we remove the clutter and we'll get the target easily. So once we observe there will be the target, so then there are some limitations there for this performance of a radar there. We would consider that. So how to improve the signal to noise ratio? Instead of that, we say that a signal to clutter ratio that will be improved, and what factors that will affect a signal to noise ratio. So now the performance of a MTI radar that will be affected by, or that will be caused by, a various factor. And these particular factors, if you consider here, so we consider first there will be the equipment instabilities, okay, equipment instabilities. Then we have internal fluctuations of clutter, internal fluctuation of clutter. Third, antenna scanning modulation. We have antenna scanning modulation, and a fourth factor that will be the limitations, limiter, or what we consider that a limiting. Okay, so that is about what we consider that a limiting factor. Okay, just like we supposed to consider that a limiting in a MTI radar. Now these are the factors. So we consider that will affect a signal to noise ratio or signal to clutter ratio. So that will be, these are the factors that will be changes the improvement factor of this MTI radar. So what are those components to be considered? We'll see one by one here. What equipment instability? So equipment instability that will be related to your oscillator or your component. Those are not stable. Okay, so generally we have considered that a MTI radar. So in that MTI radar, so we have considered that a coho and a stallow oscillator. Now that oscillator, they have changes in their phases are supposed to be in amplitude. So it will make instabilities in understanding or deriving the improvement factor. So now what will be the limitations there on the improvement factor due to the oscillator instability, and that component is nothing but a equipment instability. So we consider that while transmitting the signal, so there will be some pulse we are supposed to be transmitting, and that pulses may be varied. So we can say that pulse to pulse changes in the amplitude, or pulse to pulse changes in frequency, or pulse to pulse changes we supposed to be consider that a phase here. Okay, so we write here, there will be changes in the amplitude, there will be changes in the frequency, there will be changes in the phase. That is about when we consider that a transmitting signal, for a transmitting signal, pulse to pulse changes in the amplitude, frequency or a phase of this particular transmitted signal, that will lower the improvement factor of an MTI radar. Now, we consider that if for this particular transmitting pulse, we are getting some echo from the stationary clutter, okay, and that stationary clutter echo after sending the first pulse, and that is to be considered as a cos of omega t, and from the second pulse we get that a cos of omega t plus there will be a small variation in the phase. So then what will be the difference between these two pulses here? Okay, that is about the echo, and that echo we arrived from the stationary when we transmitting the first pulse, when we are getting the echo from the second pulse there. So there will be the variation in the phase there. So if you consider the difference between these two, so the difference between these two is nothing but what? A cos of omega t minus a cos of omega t plus del phi. Now this one is the difference, and this difference we say that del phi, it is nothing but a changes in the oscillator phase. Okay, that phi is nothing but what? It changes in the oscillator phase. So if you solve it, so we'll get the equation, okay, a cos of omega t minus a cos of omega t plus del phi. If you solve it using it equation, so we'll get that twice of sine del phi by 2 sine of omega t plus del phi by 2. This will be the equations we are getting. Now this one is the difference we are getting. That difference is nothing but what? Difference in terms of what? A small changes in the error. Okay, that is what you can say, that small phase changes there. Okay, so in that case, for very small changes in the phase error, so what will be the amplitude difference? So that amplitude difference is equal to what? Twice a sine of del phi by 2 is equal to a into your del phi. That is about a approximate. So that's why if you calculate that, what will be the limitations on the improvement factor because of instabilities in the oscillator, that will be I is equal to 1 by del phi square. So this is about this phase changes occurs in a MTI radar. We have a coho is a transmitter, and if we supposed to be consider that apply this particular improvement factor to the coho, or that will be the phase change introducing supposed to be in a power amplifier, so that may be improve the improvement factor. Okay, so that limitations can be resolved. That is about the equipment instability. Now next we consider that another factor, that is about a clutter, that is internal fluctuations of a clutter. This one is about a second internal fluctuation of a clutter. Now a clutter signal, that we say that it is about a signal or echo we have received from the stationary object. Okay. So now what are those stationary objects? There may be a tree, buildings, rain, sea, any vegetation. Okay. Likewise, there are various stationary objects, and we are getting a clutter from this many stationary objects. So now we could not say that only this particular signal we are getting from the building, mountains, hills, etc. Okay. So likewise, various components we supposed to be considered, that will be providing the, or that will reflect our signal. So we are getting the echo. So echo from all the stationary objects, and that stationary objects, we say that we are receiving this signal from the building, hills, mountains, trees. Okay, likewise. But some stationary objects, they are reflecting the signal, or we are getting the echo from some stationary object that is to be considered as a rail, or we supposed to be considered that sea, then a tree, or vegetation there. Through this, whatever the echo we are receiving through this component, that will be fluctuate with time. Okay, so we are receiving the echo from the stationary objects, it will be fixed. But some of the echoes from these objects we are getting, just like if we are receiving from the building. Okay, so we can say that building, we have a tower, hills, okay, mountain. So likewise, from this kind of a stationary object, we are getting the echo, that is stationary one. But here the kind of the echo received from this particular rain, sea, tree here. So that echo we are receiving, that will be fluctuating with time. If that echo is fluctuating with time, so then there will be the limitations, or that will limit the performance of the MTI radar. Now we will consider that what will be the clutter informations we are getting. So various target to be considered, various echo from the stationary target is to be considered, stationary object to be considered, and then we say that a performance of this particular radar there. Now if you consider that, generally we supposed to be consider that signal is to be resolved in a given particular period of a time, and then we supposed to be consider that if within this particular frame of a time slot or time signal we are getting some particular echo. Okay, so now through that we can find out what will be the echo there. So now for the given particular clutter, so what will be the a power spectrum as a function of a frequency, for the given clutter is equal to W of f, that is about a clutter power spectrum with respect to a what you can say that a frequency there is equal to, in terms of a Fourier transform of the input waveform, we can write exponential of minus a f by f0. Okay, that's about a square. And this one f0 is nothing but what? A radar carrier frequency. And this a, so that will be the parameter that depends upon the parameter depends on a clutter. Okay, so what we can say that we have the information here, and that we're supposed to consider that echo signal, it will be depending upon that a clutter information. So if you consider that this expression for the improvement factor for a n pulse canceller with a given n minus 1 delay time, so in that case improvement factor can be written as, for the n pulse cancellers nc, we can write here I of nc, improvement factor I of nc is equal to twice of n factorial, okay, fs by twice by sigma raised to twice of n1. So this will be the improvement factor for the n pulse canceller with the given delay of what? N1 is equal to n minus 1 delay line. This one is about the improvement factor. Next, we consider that the antenna scanning modulation. That is about a, you can consider that a third one. We have antenna scanning modulation. Okay, so we have the antenna scanning modulation. So now in this case, antenna will scan by target, and then it will observe the given target for a given particular period of a time or for a finite time there. So in that case, that finite time, we consider that a T0 with this antenna scans by a target. So it observes the target. Okay, it will observe the target for a particular finite time T0 is equal to NB by F is equal to theta B by theta S. And this NB, that will be nothing but what? How many number of bits or for a number of hits received, how many number of bits received for a given particular pulse repetition frequency. This FP is nothing but what? A pulse repetition frequency. And this theta B is nothing but what? A beam width of an antenna, and theta S, that will be nothing but a scanning rate. Okay, this one is nothing but a scanning. So this one is about a finite time. The target will be observed. That depends upon the number of hits received within a particular period of time. Okay, number of hits received with respect to the a pulse repetition frequency. So received pulse rate, if you consider for a given particular duration, it has a frequency spectrum, and the width of that frequency spectrum is proportional to the 1 by T0. So for given particular stationary clutter, so that T0 will be what? For a finite width of a clutter spectrum within a particular finite period of a time. If that T0, what we can say, it will be a large. Okay, if T0 is a large, so in that case, it affects the improvement factor. So that spectrum is about what? That given particular width of the spectrum is what? 1 by T0. That is about the spectrum width. And that spectrum width, we consider that to identify a stationary object. So for given particular stationary object, there will be a finite width of the spectrum within a particular period of a time, finite time given for the a target. Okay, so we can identify the target. If that particular clutter spectrum is large, so then it will affect the improvement factor. So we consider that this limitation is called as a scanning modulation or a scanning fluctuation. So the limitation to the improvement factor that will be caused by this antenna scanning, we can write here improvement factor I1S, that is about a single canceller, NB square by 1.388, that is for the single canceller. Okay, this one is for the a single canceller. I1S is equal to NB5 NB raised to 4 by 3.852, that will be for the double canceller. Okay, so we can consider that. So what will be the information we are getting while scanning? Okay, and that scanning information that will limit the what will be the finite time limitations, or we can say that a spectrum there, and that will affect the performance of a scanning there, antenna scanning. So if we broaden the given particular spectrum, so in that case, there will be the limitations for the antenna scanning or limitations to understand the information. So for this particular purpose, we use a digital processing so that this modulation can be improved or these limitations can be improved. Then another one, limiting in MTI radar So generally a limiting we consider that is to be used in a MTI processor. So generally we consider that a limiter is used in a IF amplifier so that it will limit whichever the echoes we are receiving from the a clutter there. Okay. So there will be large clutter we are receiving or large clutter echoes we are getting, and that large clutter echoes that can be limited by this IF here. So generally that ideal radar or ideal MTI radar that will reduce a clutter to a level of a receiver noise, or you can say that a clutter will be reduced to a comparable level to the receiver noise. If that level that will be relative to the noise, if we set to the higher value than the improvement factor, then they then that particular clutter having the higher value and at a display, so we are not able to detect whether there will be target or what. So on a display we could not get any information, and we are not able to detect or we are not able to see the any information. So that is nothing but what even the target is present, because of that large clutter value we are getting the echo, and that's why we say that that will be the false assumption of a given particular pulse, or we can say that there will be a false prediction. Okay. So or we are not able to detect there will be the given pulse. So this one is about a limiter, or we can say that a limiting conditions of the radar, and that will be improved by considering a later values of the given particular target or that particular echo receiving from the clutter that will be filtered. Okay, so we can consider that a single delay line canceller, double delay line canceller, and that will remove the clutter information. So these are about the limitations to the MTI performance. Next we talk about that difference between that MTI and a pulse radar. So we have considered that MTI radar, even we have seen that a pulse Doppler radar. Okay, so in that case, both the cases we have seen that there will be a shift in the frequency, and both are depending upon that a pulse repetition frequency. But a small difference or small variation here, a moving target indicator, if you consider that we supposed to choose a PRF in such a way that there should not be any range ambiguities occur. But there are another issues present in MTI radar due to the given PRF value. There will be the Doppler ambiguities, or we can consider that at a given particular pulse repetition frequencies, there will be the a blind speed. if you consider that this particular limitations, if you overcome or if you forget about this particular limitation, so MTI radar is better to detect the moving target, and we can remove the whatever the blind speed we have or a blind target we are getting. So improvement in the MTI radar with the given PRF. So we consider the various values of a PRF to avoid the blind speed from the moving target. But if you consider that a pulse Doppler radar, so there are various approach in the pulse Doppler radar. So there will be the range ambiguities occur. There will be a Doppler ambiguity is there. So to avoid it, we can supposed to consider that high pulse repetition pulse Doppler radar, and that will be used to understand or to limit the performance, or that will be improve the performance of the radar there. So there are the various difference with respect to the how this radar will avoid a blind speed, or how this will be identify the target. Both are used for detecting the target. This one is for the detecting the target. But if you consider that a range and all, so there may be the ambiguities in range. So what will be the pulse repetition frequency we consider to avoid the blind speed? Because there may be variation in the pulse repetition frequency, so that we can avoid a blind speed or a blind target. So based on this pulse repetition frequency, there are the types of pulse Doppler radar. In that case, we consider that a medium PRF, or we can say that a high PRF. And these values, if you consider a different values of a PRF, that are nothing but the types of a pulse Doppler radar. So the pulse Doppler radar, they differ in the values of a PRF, and they differ based on that, they differ with a ambiguities there. And that what type of ambiguities are there? The ambiguities in terms of a range ambiguities or a Doppler ambiguity, or we can say that no range ambiguities, but there will be Doppler ambiguity. If you consider that the MTI radar there, so in MTI there will be a no range ambiguities, but there will be the many Doppler ambiguities. So then there will be the blind spot. So in the pulse repetition radar, if you consider that, so there will be the many range ambiguities and no Doppler ambiguity. Only these are the difference in the MTI Doppler radar and a pulse Doppler radar. So now next we proceed to solve one of the numerical there. What will be the blind speed that is to be obtained here? Now an MTI radar is operating at 10 gigahertz with a PRF of 1000 hertz, with a PRF of 1000 hertz, calculate the lowest 3 blind speed. So to calculate the lowest 3 blind speed, so what will be the answer for this? We can calculate that blind speed is equal to what? Vn is equal to n lambda fp by 2. So f is about your frequency. We consider that is about operating at 10 gigahertz. We can say that 10 into 10 to the power 9. Okay, we have 10 gigahertz there. Okay, that is about a frequency, or you can say that 10 to the power 10 here hertz. So we can calculate that a lambda is equal to c by f. If I solve it, so I'll get the lambda, that is about a 0.03 meter here, and then put that in the equation. That is about Vn. Instead of that, we say that 1, n will be a 1. Okay, if you consider that n will be a 1 here, into a lambda, that is about a 0.03, into the pulse repetition frequency is about 1000, divided by 2. So if you solve it, we will get that 15, that is the speed meter per second. And if you convert into the kilometer per hour, we say that 15 into 60 into 60 divided by 1000. Okay, you consider that this way here. So we will get that 54 kilometer per hour. So that is about a first blind speed. That is about a 54 kilometer per hour. Then a second, if you solve through this way, twice of V1, what we are getting here, that is 2 into 54 is equal to 108 kilometer per hour. Similarly, V3, twice of V1, 3 into 54 is equal to 162 kilometer per. So this way we can find out a Doppler speed runner. So these are about the radar, and we need to find out what is the blind speed for the given radar. And this way we can find out what will be the speed of the radar. Okay. So now we will consider that suppose any traffic control station wanted to measure that speed of the car. So what will be the speed of the car there? For that purpose, for the speed of the car, we are supposed to know that a Doppler frequency shift. So what will be the Doppler frequency shift for a given particular frequency here? That is to be considered. And then through that we'll get the speed of the car there. So we need to know what will be the Doppler frequency shift and what will be the operating frequency there. And then we can obtain the what will be the speed of the car there. So lambda is nothing but what is equal to what is C by F, that is about the frequency of the radar, and then E of D is nothing but the a Doppler frequency shift, and then we can find out the speed of the car. That's all about the radar system. Thank you all.